Okay, good morning, everybody.
Morning.
Okay, welcome aboard this morning. Does anybody have any questions?
Can you go over writing half reactions?
Yes.
Thank you.
Okay, let me see if I can find. There we go.
I have an example, if that helps.
Yes, I'm actually bringing one right up here. Okay, aqueous chromium 2. Okay, all right. So mostly what we spoke about when we talked about reduction oxidation reactions were assigning oxidation numbers. So for example, if you have some kind of reaction, and let's take iron, for example. And let's say it reacted with oxygen. To form iron oxide. And I guess we can balance it. There we go. One method of analyzing a redox reaction is to assign oxidation numbers. So what you'd do is you'd say, okay, well, let's look at iron. It has a charge of 0. It's an element. So that means its oxidation number is 0. And oxygen, same thing. That's an element. So its oxidation number is 0. And then on the product side, you take a look and you say, well, we don't know what iron is in a compound because there's no rule for it. But there is a rule for oxygen, which says that it's in a compound or a polyatomic ion, it's -2. So then we say, well, for FeO, it's got to add up to 0. So that means if the oxygen is -2, the iron has to be +2. And so that's one way to analyze redox reactions. Another way is to say, well, what if we have iron as a reactant? And we take a look at what it turns into. It turns into Fe+2. We could ask ourselves, well, what's another way that we could analyze that? And that's to use what's called the half reaction method. So it's very simple. What you do is you say that a redox reaction involves an atom transferring one or more electrons to another atom. And so when that happens, the first atom now becomes positively charged and the second atom becomes negatively charged. So we can represent this process as a transfer of electrons. So here's how you go about it. Very simple. What you do is you first check to make sure that you've got the same number of atoms on both sides, just like you would normally balance an equation. So it looks like there's one iron atom and one iron ion. But notice this one has a different charge than this one has, right? This one has a charge of 0. If there's nothing written next to it, it says 0. And then on the product side, it's +2. We know that a redox reaction involves transfer of electrons. So the only issue left is to figure out where to put these electrons. So the way we do this is we use the symbol of an electron as an E negative, right? The negative is a superscript. So that means it's an electron and electrons are negatively charged. What you do is you add these to the more positive side of the equation. Okay, the more positive. So let's look at this equation here. This equation has a 0 charge on the left side, and it has a +2 charge on the right side. So this is the more positive side, right? Because it's got a positive here. So what you do is you add the electron to that side, and then the number that you add is just how different are these charges. There's a difference of 2, right? +2 is different from 0 by 2. So you just add 2 electrons to the more positive side. So this is called a half reaction. FeS, arrow, Fe2 plus 2 electrons. What this says is the iron atom, this one over here, is essentially losing 2 electrons. They're being ripped off of the atom. And when that happens, if you think about it this way, iron has 26 protons because it's element number 26 and 26 electrons. If you remove 2 electrons, so these are the ones that are removed, now it'll have 26 protons and 24 electrons. You're removing 2 electrons. So now if you compare the, protons, electrons. Okay, so now if you compare these two numbers here, essentially what has happened is the iron has lost 2 electrons, so it'll have a charge of +2. Okay, so there's one. Let's take a look at another one. Chromium.
Can you do one where it goes from, 302 to 03?
Yeah, let me do the chromium one first.
Okay.
Okay. So chromium 2 is oxidized to chromium 6. This is a Roman numeral 6. Write the half reaction for this process. So chromium, the symbol for chromium is Cr. Right? Just look that up. It's element number 24. And then the number in Roman numerals is technically, it's called the oxidation state, but you can think of it as just being the charge. That's what the charge of this particular ion is. So if you see Roman numerals, that means it has a charge. And Roman numerals are generally used only for positive charges. Notice this is a metal. Metals don't tend to form negatively charged ions, only positive. But if you see a Roman numeral, that means it's a positive charge. So chromium 2. So you can write that as 2+. And then it says it's oxidized. So is oxidized means is losing electrons. And that means you're turning into something else. If it says it's getting oxidized, that means it's reacting. Oxidation is a type of reaction. So you write the arrow. And then you say, what is it being oxidized to? Chromium 6. That's 5 plus 1. That's 6. So you write Cr plus 6. Okay. So remember, the Roman numerals are the positive charges. And then you say, okay, which side is more positive? It looks like the product side is more positive, right? +6 is more positive than +2. So you add the electrons to the more positive side. What's the difference between the charges? 2 and 6 is 4. That's a difference of 4. So you add 4 electrons to this side. In oxidation, the electrons are on the product side. Okay. In reduction, it's the opposite. The electrons are on the reactant side. Okay. So electrons on the product side for oxidation. You just remember one and then you can remember the other. So let's take a look at one that might be a little bit different. You said you want to look at one that's oxygen. Let me see if I can find one here with oxygen. Some of them are metals. That one could work actually. Here's me to show you, what is this? Gaseous dichlorine. Let's take a look at one more. Oops. There we go. Okay, so let's say we're going to write the half reaction. For oxidation. So remember oxidation, so that means the electrons will be on the product side of aqueous chloride ions into gaseous chlorine. Now this one, there's some pieces of information that you have to kind of remember from earlier topics. So let's go over this one. Chlorine chloride. So let's look and see where that element is. It's column 7A. And if you remember, in column 7A, the ions are -1. That's their charges. So chlorine as an ion will be Cl negative, right? So you only know that because you go to the periodic table. But there's another issue that's particular about chlorine, and that's the issue back in chapter 3 about the diatomic elements, right? Some of the elements are diatomic. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So that comes up here again because it says that it turns into gaseous chlorine. That's chlorine right there, right? So that means it's a diatomic. So with this one, there's two kind of details that you have to remember. One is what's the charge of the ion, and then the other one, what is the formula for the element? So let's go through it. Half reaction for oxidation of aqueous chlorides. Okay, so chloride, Cl negative, aqueous, into gaseous chlorine. So Cl2 with a G. Now with this one, you have to remember the first step is you balance the number of atoms. We're going to balance the number of electrons when we get to that stage. But first, we have to balance the number of atoms. So there's only one atom here, right? It's Cl, so there's only one. Over here, there's two atoms, Cl2. So that means we have to put a 2 on the reactant side, right? That is going to affect the number of electrons, right? Because each atom transfers electrons. So if you have more than one atom, you transfer more than one electron. So let's take a look at it. How do we figure out the charges? Well, this is an element. So it has a charge of 0. There, you can, for yourself, you can't put this into Alex, but you can, for yourself, you can put a 0 there. That's what the charge is. If it's an element, it has no charge. But over here, we have a charge, which is -1, but there's 2 of them. Each one is -1, so that's -2. So what do? We add the electrons to the more positive side. 0 versus -2, the 0 is more positive, right? -2 is more negative. So we add 2 electrons. And let's remind ourselves, okay, we said that oxidation, the electrons are going to be on the product side. Well, it says it's oxidation, and we did put the electrons on the product side, so that looks pretty good. Looks like we got it. Okay. Kate, did you want, what was the one that you wanted to look at?
Aluminum plus oxygen creates Al2O3.
Okay. So now we're going to take it, and what do they want? What do they want you to do for this one?
Oxidation and reduction.
They want you to do both. Okay, now, here's the thing about redox reactions. Redox reactions are actually 2 reactions. Reduction, oxidation, right? There's actually 2 reactions occurring. So reduction is where electrons are gained. And then oxidation is where electrons are lost, right? So just like with oxidation, the electrons are on the product side, with reduction, the electrons are on the reactant side. So there's 2 separate equations for a redox. So here's how we go about it. The way you do it is you take your first reactant, so that's aluminum, and then you take your second reactant and you write that as a separate equation. Okay. Now on the product side, notice they're together That makes it a little more complicated than the examples I showed you. What do we do if they're together? What you do is you treat a compound as ionic compounds. And remember, an ionic compound has a positive ion and a negative ion, right? That's what an ionic compound is. And in the beginning of chapter 4, when we did precipitation reactions, we learned that an ionic compound can be separated into separate ions, just like salt. So what you do with aluminum oxide is, since it's a compound, is you break it up into separate ions. Now, which ions are it going to form? Oxygen, sulfur, selenium are in group 6A, so they're going to be -2. Okay, so now what you can do is you can say, okay, on the product side, we're going to have oxygen, but treat it as an ions. Okay, so here's how you go about that. Oxygen is -2. Okay, and then you ask yourself, how many are there? Well, there's 2 over here, and there's 3 over there, so that's contradictory. How many are there? The issue here is that they gave you the equation. They had you write the equation, but it's unbalanced. It's not a balanced equation. So that means at some stage it's got to be balanced. Okay, so we'll go through that next once we get these sort of set up. What about the aluminum? How do we deal with the aluminum? This is about as complicated as an ionic compound can be. You've got 2 ions and 3 ions. How do we deal with that mathematically? What you do is you say you've got 3 oxygens, so that gives you -6. So that means that you've got 2 aluminums has got to be equal +6, right? The positive has to equal the negative, but 2 of them equal 6. So that means each one is +6 over 2, which is +3. Now, some people will just memorize. They will memorize certain ions. They'll memorize that silver is +1, zinc is +2, and aluminum is +3 from the periodic table. It's actually kind of interesting. What you get is aluminum, and then zinc is right below it and over 1. And then silver is, am I right? Okay. It's 13, 29. And so I have that wrong. It's, let me save this. I want to show you these ions because most chemists will just memorize this. Element number 13 is aluminum. And then if you go down 1, what does that come out to? 13.
Zinc is 30.
Zinc is 30, thank you. So 13, and then 30 is over here. And then silver's below that over here. 47. What they do is they just memorize. This one is +1, this one is +2, and this one is +3. Okay. I don't expect you to memorize those, but many people just, that's what they do. That way they know they don't have to do any mathematics to figure out what aluminum is. They don't have to do any arithmetic to figure out what zinc is, and they don't have to do any math to figure out what silver is. They just memorize those 3. But you don't have to memorize them if you can figure them out. Because what you can do is you can say, if the oxygen is -2 and there's 3 of them, that's -6. That means the aluminum has to be +6, but there's 2 of them, so each one's got to be +3. So now we can do the aluminum. +3. Okay. Now what you do is you say, okay, which side's more positive? This one's more positive, so we add the electrons to that side. There's no charge on the aluminum on the reactant side, but there's a charge of +3 on the product, so we add 3 electrons. And remember, oxidation is where the electrons are on the product side. Now let's do the oxygen. There are 2 oxygens here, so we need 2 oxides there to balance the oxygens. Now, if you look at the charges, each one's -2, so that's -4. There's no charge on the reactant side, so the more positive side, if you have a negative on one side and a 0 on the other side, the 0 is more positive. So now we got to add 4 electrons. So that's going to go on the reactant side, and that's going to be reduction. Okay. So when you do the ALEX problems, they just want you to draw out those half reactions. They don't, I believe, expect you to then balance those 2 half reactions. It can be done. It's a pretty simple step, but I don't think they actually want you to do that one. Okay. Let me save that one. Let's see if there's another one just like it. There we go. All right. Identifying. Okay. Yeah. I can't find that particular problem that you just brought up with the aluminum and the oxygen on ALEX.
It was in the practice exam.
Oh, it was in a practice exam. Okay. So let me see if I can find one like it then. Writing half reactions for a metal, non-metal reaction. Here we go. Okay, here's one. So this one says, study the chemical reaction. Ca plus Cl2 goes to CaCl2. And then it says, then write the balanced half reactions. And then they have you do oxidation and then reduction. Okay. So here's a little tip. When you do a chemical reaction, a redox reaction, the metal is always oxidation and the non-metal is always reduction. Okay. In nature, that's how it works in nature. Metals get oxidized and non-metals get reduced. So here's what we'll do. I'm going to take the calcium. You really, in a sense, what you have to do is you have to break these up into ions. So let's do the breaking up of ions first. Calcium is in group 6A, so that means it has a charge of +2. Chloride is in group 7. I'm sorry, this is group 2A. Calcium is in group 7A. So that means it has a charge of -1. Okay. So that means we can break this up into calcium +2 and chloride -1. Okay. So let's do the calcium first. Calcium is the metal, so I'm going to put it in the oxidation, and it's going to get converted into Ca+2. Okay. Chlorine is on the reactant side here. It's the nonmetal. And it's going to get converted into Cl-. Okay, so there's your oxidation and there's your reduction. Now, let's do the following. Let's balance with electrons. More positive, so that means you add the electrons to that side. How many? 2. This on the reactant side is more positive than that one on the product side. However, there's 2 of them, so that means we need to balance that first. Remember, with diatomics, you're going to have to add a 2 there. So now this is more positive. That means this is more negative. So you add the electrons to the more positive side. How many? 2 times -1 is -2. So you're going to add 2 electrons. Okay. Now they could be a little bit tricky and they could show you a reaction that's not typical, but it looks like they don't do that. So that's fine. Looks like everyone that they have you do is following a standard format. Okay, that's good. Okay. Let me show you one more. Suppose you have...
What I'm having a hard time understanding is when and why it goes from Cl2 to 2Cl, or from O2 to... that's what's confusing me, is how the coefficients versus the subscript functions in these equations.
So remember, when we talk about molecular compounds, so an example would be glucose. What we said is that glucose dissolves in water. Sugars dissolve in water very nicely. But when they dissolve, really all they do is they form molecules dissolved in water. So the chemical formula does not change when you dissolve sugar. It's the same substance. And you can tell that this is true by taste. If you taste a piece of sugar, it tastes the same as sugar in water. But ionic compounds are different. Ionic compounds, when you dissolve them into water, they break up into separate ions according to their position in the periodic table. That's what's nice about the periodic table. What that tells us is that if we have sodium, it doesn't do this. It doesn't turn from Na2 into Na2+. That doesn't happen. Okay. What you have to do is you have to say, well, wait a minute. This is sodium. It doesn't matter how many are in the formula. They're actually going to break up into separate ions. And here's the notation that we use. Think of a bicycle. A bicycle has 2 wheels on it. But if you disassemble the bicycle, you don't get a double wheel. There's no such thing as 2 wheels stuck together in a bicycle. That's not what happens. What happens is you get separate wheels. And so the notation that we use for that is 2 in the front, 2 wheels, and not a wheel dimer. It's called a dimer, where the 2 are stuck together. So the reason that for this one you put the 2 in the front is because a chloride ion, Cl-, does not exist like this. It just doesn't exist. Not found in nature. It's individual ones, separate ions. And the way you'd show that is by putting the number in the front. So for example, aluminum chloride. That's going to break up into +3 and 3 chlorides. Iron chloride. That's going to break up into iron and 3 chlorides, separate ions. Zinc chloride. There's a 2 there, so you get 2 chloride. These are separate. Remember in math, x plus x plus x is equal to 3x. So if these are separate, you write the 2 in the front as a notation. That's what we're doing. I mean, you could, in theory, you could write it this way. You could write Al plus 3 plus Cl minus plus Cl minus plus Cl minus. But that's not how it works.
But oxygen always remains O2.
No, because remember we did Al2O3? It goes to Al plus 3 plus 3 O negative 2s. So if you have a formula with a metal and a non-metal, that means it's ionic. So in ionic compounds, they are ions and they follow very rigid, pretty rigid actually, F minus, Cl minus, Br minus, I minus. They all form negative ions, but they do not form F2 minus. That doesn't get seen. They do not form Cl2 minus. That's not observed. They form individual monatomic ions. Mono means one, meaning that they are one individual ion. Same thing with group 6A. O negative 2, S negative 2, Sc negative 2. Each one of those is going to be O negative 2. So if you have more than one, you put the number in front. That means there's 2 of them, but it does not form O2 negative. That doesn't happen, except under exotic situations. Okay, so -1. So those prefixes got to go in the front. They got to go in the front for any of these elements here. I'm trying to think if there's any, when people get intravenous fluids, whether calcium is ever added. I imagine that it happens. They probably have to give you calcium sometimes. So if you take calcium, for example, calcium chloride, and you dissolve that into water, you get 2 chlorides. Okay. Let's see. Yeah. So when I look at the possible examples of those problems, the anion, the negatively charged ion, is always either a group 6A or a group 7A. They're not doing any unusual ions. They're just doing group 6A and 7A. So that tells you what the charges are going to be. Okay, good. Any other problems anybody wants to look at? Okay, so I guess what I wanted to do then was probably in the next few days, you're going to be starting on the exams. Oh, by the way, the exams are now graded for exam 1. So when you take the exam, Alex is only capable of giving you full credit or no credit at all for a question. So sometimes what I notice is that it can be pretty harsh on things like significant digits, significant figures, and notation sometimes. So for example, you might put the symbol for the unit in the wrong place or something like that. So usually what I always do is after the exams are submitted, I go back and look for and adjust the scores. So your original score, let's say you get an 80, that might get adjusted and you might get more credit. So take a look, you know, a few days after you take the exam and see if it got adjusted. Okay. The next subject is chapter 5, which is called Thermo Chemistry. So what I want to do today is talk a little bit about the first topic of that chapter, because it's a little unusual and a little challenging for most people. So let me go through it a little bit. Okay. Thermochemistry. Thermo means temperature. And temperature is related to heat. They're not the same thing, but they're related to each other. And of course, chemistry is the rearrangement of atoms at the molecular level. So really what we're doing here is we're looking at how chemical reactions affect temperature by transferring heat. Okay, so there's some terms here that we're going to need to be familiar with. And the first thing to say about this topic is that, unfortunately, everyday language that we use to talk about heat is wrong. We have generally people have a very incorrect way of talking about what heat is and how it's related to temperature. And even if you read biology textbooks, the understanding of the authors of how heat and temperature work are generally incorrect. Chemistry textbooks are much better at explaining it, not at explaining it, but getting it correct. Physics books are even the best at getting it correct. So be careful where you read and find your information, because everyday language can get you an incorrect understanding of what's happening. So let me talk first about what temperature is and what heat is, okay? The idea is the following. What we observe is that if you take an object that is, let's say, 100 degrees C, 100 degrees Celsius. Now, I picked that temperature for a reason. 100 degrees Celsius is the temperature that water boils at under normal conditions. So if you put water on a stove and heat it up, the water will get hotter and hotter and hotter until it reaches a temperature of 100 degrees Celsius, and then it will start to boil. So we call that the boiling point of water. The boiling point of water is a temperature that water boils at. And interestingly enough is that when you boil a substance, it doesn't have to be water, it could be alcohol, it could be anything. When you boil a substance, its temperature remains constant until all of the material has disappeared. So if you were to stick a thermometer into a pot of boiling water, what you would find is, even though you continue to add more and more heat, it does not change temperature. It will remain constant at 100 degrees C, and all of that heat that you're putting into the water will just cause the water to boil off. Okay? So you can heat substances and make them hotter up to a point. But once you get to the boiling point, you can no longer change the temperature of that substance. It will just boil away. So let's say that I have a piece of metal, and that metal has been brought to 100 degrees C. It's right at the boiling point of water. Metals boil at much higher temperatures than 100. And then what I do is I stick it to where it's in contact with another piece of metal. So this is a piece of metal. And this is another piece of metal. And this one is at 0 degrees C. Now that temperature is special too, because 0 degrees C is what's called the freezing point of water. This is the temperature that water freezes at under normal conditions. So I picked 2 temperatures just so that we can be aware that there are significant temperatures in terms of the properties of water. So now here's what we're going to claim happens. Over time, if you observe these 2 metals, now what I'm going to do is I'm going to assume that the masses are the same. So, let's say this one weighs 100 grams and this one weighs 100 grams and they're the same metal. So it doesn't matter what they are. It could be iron, could be gold, could be silver, could be copper, but they're the same metal. If you give it enough time, what will happen is the first metal will be 50 degrees C and the second one will also be 50 degrees C. So this one has gotten cooler, right? It went from 100 down to 50. And the other one has gotten hotter. It's gone from 0 up to 50. What we would claim is that this process involves a transfer of heat. That's the terminology we would use, that heat has been transferred from the hotter object, the hotter metal, to the colder metal. And this is something that is observed in nature, which is that if you have a hotter object and you put it in contact with a colder object, the hotter object will get colder and the colder object will get hotter. It goes in only one direction. We do not observe that if you take a hotter object and put it in contact with a colder object, that the hotter object will get hotter and the colder object will get colder. Imagine if it worked that way, right? If you took like an ice cube and you put it in contact with boiling water and the boiling water got hotter and the ice cube got even colder, that is not observed ever. Statistically, virtually impossible for that to occur. Hotter objects transfer heat to colder objects only, okay? Now, what is this heat? I mean, notice what I'm saying. We're transferring heat. What does that mean? All we know at this stage is that one got hotter and one got colder. But what is this quantity that we call heat? So what we're going to claim is heat is when atoms or molecules transfer kinetic energy to other atoms. And I'm going to, again, repeat this point that the hotter atoms are going to transfer the energy to the colder atoms, not the other way around. Statistically, it just doesn't happen, okay? So what is this idea of kinetic energy? Kinetic energy is the energy of motion. If we look at matter at the atomic or the molecular level, atoms and molecules are bouncing around and moving. So I'm going to represent that motion because this is a static drawing. I'm not drawing an animation. I'm drawing just a diagram. Motion we can represent using arrows. So if I draw an arrow, that means that that atom is moving in some direction. What is found is that atoms in general, if you leave them to their own, leave them to themselves, they move pretty randomly. There's random motion. So if you take, for example, a glass of water and you were able to picture all of those molecules in the water, you would find that they're moving pretty randomly. So one molecule might be moving in one direction, collide with another, and then move in another direction, but there's no overall directionality to that motion. Okay. So when an object has motion, it has what we call speed, right? So for example, an atom could be moving, let's say, 50 miles per hour in this direction. It has a speed, but we're going to use a different term for that. We're going to use velocity. And there are unfortunately, there are different symbols used for velocity. You might see V for velocity, which kind of makes sense to me. Velocity starts with a V. More likely, you're going to see in chemistry classes, you're going to see a U. And that's used for historical reasons. So this one right here, the U is more common. Okay. Velocity, I'm not going to get into it too technically. It's really an issue of how you define motion. Velocity is the speed, how fast something is moving, but it also takes into account what direction it's moving. So for example, if an atom is moving 50 miles per hour in this direction, that would have a different velocity than one moving 50 miles per hour in this direction. The speeds are the same, but the velocities would be different. So we're going to use the term velocity, but we're really going to be talking about speed, how fast they're moving. So these atoms are moving in different directions pretty randomly at different speeds. That would be called kinetic energy. Kinetic energy is the energy that an object has when it's moving. So this is the energy an object has when it is in motion, meaning it's moving. Okay? Again, different symbols are used for this. I will use a capital E for energy, and then I'll put a little K underneath it for kinetic. But you will see different symbols. Sometimes people use KE for kinetic energy. Sometimes people just use a K for kinetic energy, but it's some form of energy. Okay? So now if an atom is moving in this direction, and let's say its speed or velocity is 100 miles per hour, and now another one is moving, let me erase that, at only 50 miles per hour, they would have different kinetic energies. Okay, they would have different values of kinetic energy. So let me give you the equation. The kinetic energy of a particle is 1/2 times the mass times the velocity squared. So it's whatever the mass of the particle is, or the mass of the object, times its speed or velocity squared. Okay, times 1/2. So let me write that as a formula. 1/2 mu squared. This will really be important in chapter 10 when we get to gases, but it's also something that we talk about here. So an object that has a large velocity, okay, so objects with large velocities, I'll just use speeds, we'll use them interchangeably, have large kinetic energies. right? And if you think about it, it makes sense, right? The idea of a bullet, for example, fired from a rifle, is that a bullet's actually a very tiny thing. It doesn't have very much mass at all. It weighs a little bit like a pencil. But because it moves so fast, hundreds of miles an hour, it has enormous energy within it, right? The same is true for an airplane. An airplane might be able to move 500 miles an hour, so it has enormous kinetic energy. The amount of kinetic energy an object has is largely determined or dependent on how fast it moves. If two people are running, the person that's running faster generally has more kinetic energy. Okay? It depends on mass as well. The more massive something is, the more kinetic energy it has. But it's even more dependent on velocity because of that square. The fact that you're squaring it makes it more important mathematically. So now let's talk about heat. What I'm going to do is I'm going to draw a picture at the molecular level of these two pieces of metal. So here's the hot object. And I'm only going to show the atoms that are near the surface here. Okay. And now let's put it in contact with the cold metal. So here's our atoms here. Here's the explanation for why heat transfers from hot to cold and not the other way around. If we say something is hot, that means the atoms are moving fast on average. If we say something is cold, that means the atoms are moving slower. I'll just write slower. Faster and slower. Let's use those terms, okay? So these atoms over here are moving very rapidly. Now, how can metal atoms move? Metal is a solid. They vibrate. So if you take a piece of metal and you look at the molecular level, the atoms are vibrating. If they vibrate very rapidly, that means they're moving very rapidly and they have a lot of kinetic energy. If something is colder, that means they're vibrating more slowly. They're not moving very quick, so they have less kinetic energy. So here's what happens. If you've ever played pool, if something is moving fast and it collides with something that's moving slow, what will happen is when the collision occurs, the object that was moving slower will now move faster. And the object that was moving faster will now move slower, right? Think of a collision with a wall. If something collides with a wall, the thing that's moving very fast over time will slow down after it collides. The wall, however, will now start to move. So here's what happens. When you take the hot piece of metal and put it in contact with the cold metal, these particles here are moving very quickly. So they will start colliding with the atoms on the cold object. And these cold atoms will start moving faster. The hotter ones will start moving slower because they're transferring energy to the colder atoms through these collisions. It's all about collisions. So now these ones are going to start moving faster. And these ones are going to start moving slower through countless collisions, trillions of collisions every second, okay? So that we call transfer of heat.
Professor, I have a question. Is it always the temperature will be balanced between those two metals?
You mean that the temperature will be the same at the end?
Yes.
No, it actually depends on what, if they're different metals, they will have different temperatures. And if they have different masses, they will have different temperatures. So it only works that the temperature will be the same if they're the same metal and the same mass.
Got it. Thank you.
We'll get more into that later on. Okay, so here's our idea of what heat is then. When we say something is heat, what we mean is the faster objects have collided with the slower objects and transferred kinetic energy to those slower objects. So when we say transfer of heat, really what we mean is a transfer of kinetic energy. So again, if you've ever seen a car crash, if you got a car that's moving 50 miles per hour and you got a car that's stationary, meaning it's not moving, what happens? The car that's moving 50 miles an hour hits the car that's moving 0, and this one will speed up. It'll go faster, and the one that's going faster will slow down, right? It's transferring kinetic energy to the slower object. So if you took a car that's moving 50 and a car that's moving 0 and collided them, you wouldn't expect the car that was moving 50 miles an hour to now be moving 60 miles an hour, and the car that was moving 0 to move even slower than 0, right? Because that's physically impossible. You can't move slower than 0. So that's what happens with these atoms. They collide with each other. These ones get faster. These ones get slower. And if you were to measure the temperature, here's what happens. This one started off at 100. This one started off at 0. After enough of those collisions have occurred, this one will be colder. And this one will be hotter. And the reason this one is hotter is because the atoms are moving faster now. Okay? So that's an important aspect as well, this idea of temperature. Temperature is a measure of how fast atoms are moving in a substance or in a material. Okay? How fast are they moving? And interestingly enough, you can actually measure this property, which we call temperature, with some very primitive technology, right? Almost no one uses this anymore, but all you need is a little glass tube with a liquid in it, in a very narrow capillary, right? You put a little liquid and you make this out of glass. And what happens is if you put it into something that's hot, the collisions occur on the glass, and then the liquid starts to rise, right? It gets higher and higher. We call that a thermometer. Very primitive, right? If you think about it, it doesn't take much technology to do that. Take a piece of liquid and a piece of glass, but it actually works. And it works because what's happening is when you put it in the hot material, those atoms are moving very rapidly. They start colliding with the glass atoms and transferring kinetic energy to those glass atoms. So they start moving faster. They then start colliding with the liquid. The liquid has nowhere to go when it starts moving faster. It can't move to the sides because it's in a little capillary. So the only thing it can do is start spreading out upward. And so it starts rising up higher and higher. But it's a transfer of kinetic energy between atoms. Okay. So heat, transfer of kinetic energy of atoms, and temperature, a measure of the kinetic energy of atoms. Okay. Well, that was pretty cool. All right. So be careful out there. When you read up on heat and temperature, it can give you some sort of odd interpretations of what it is, but that's a pretty good interpretation of what heat and temperature are. Tomorrow, what I would like to do is spend some time talking about a very particular type of problem, which is the problem of a gas cylinder. Because in the Alex homework for chapter 5, quite a few of the problems involve this issue of the gas cylinder. So I'll talk about that tomorrow so that you can really get going on those. Probably some of you are going to be continuing to work towards your second exam this week. But be careful, you know, try to keep up with the homework for chapter 5. So I would recommend trying to take the exam, you know, by Wednesday or so that you really can focus on chapter 5. But of course, it's up to you. You have the whole week to take the exam. Okay. Very good. Thanks for coming today. I just wanted to add today just so that we could get into some of this new material because we're so accelerated this 6-week period. And have a great week. Reach out to me if you have any questions. And I will post this to YouTube in about an hour or so. So have a great day, everybody.
Thank you, Professor. Have a good day.
You have a great one.
Thank you.
Thank
Thank
you.
you, Professor.